In this lecture, I am going to tell you about why we use AVL trees, and then we will learn about the proof of time complexity of AVL trees. So, since AVL tree is a binary search tree, its time complexity will be order of h, where h is the height of the binary search tree. But in the worst case, the binary search tree could be a skewed binary search tree, and hence the cost of operations can go up to order of n. And to overcome this time complexity, we use AVL trees, and in that case, the operations take order of log n time. So let's learn how we get order of log n time complexity in AVL trees. So let's assume that h is the height of the AVL tree, and let's say f of h is equal to the minimum number of nodes in the AVL tree. So let's prove this with the help of induction. So when h is equal to 0, the minimum number of nodes will be only the first node, which will be the root node, and hence f of 0 will be 1. When h is equal to 1, the minimum number of nodes could be 2, that is the root node and the child could be at the left side or the child could be at the right side. This will be h is equal to 1, and so the minimum number of nodes will be 2. So f of 1 is equal to 2. Now let's see what will be the minimum number of nodes when h is equal to 2. So this node can have one node. We can say this will be the minimum number of nodes. But if you see, this node is balanced, this node is balanced, but to follow the properties of AVL tree, this node should be balanced. So we will add one node here, and as you can see, the difference between the height of the left subtree and the height of the right subtree, the modulus of that is less than or equal to 1 for each of the node, and hence this tree is also balanced. Also, it is a binary search tree, hence this is an AVL tree. So the minimum number of nodes will be 1, 2, 3, 4. So f of 2 turns out to be 4. Now let's look at when height is equal to 3. When height is equal to 3, I can add one more node here. So this is balanced, but this node becomes unbalanced, so we have to add one node here. So this is now balanced, and since now this node also becomes unbalanced because the height of the left subtree is 0, 1, 2, and the height of right subtree is only 0, so we'll have to add one node here as well. So now the height of this node becomes 0 and the height of this node becomes 1. So difference between the left and the right subtree modulus is less than or equal to 1. In this case it is 1, and hence height is equal to 3, and it is a balanced AVL tree. In this case, the minimum number of nodes is 1, 2, 3, 4, 5, 6, 7. So f of 3 turns out to be 7. Let's do it for one more case. So when h is equal to 4, let's see what will be the minimum number of nodes. So our root node, one here, one here, one here, one here, one here, one here, and now we'll add one node here. So this is balanced, this is balanced, this is unbalanced, so we'll have to add one node here. This is unbalanced, so we'll add one node, let's say here. This is also imbalanced, so we'll add one node here. But now this becomes unbalanced, so we'll have to add one node here. So then the minimum number of nodes will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So f of 4 turns out to be 12. So now if you look closely, by induction we can say that f of h is equal to 1 plus f of h minus 1 plus f of h minus 2. So let's see if this formula holds. So if for f of 0 we'll say it is 1, for f of 1 we'll say it's 2. Let's find out for f of 2. So according to this formula, f of 2 will be 1 plus f of 1 plus f of 0, which is equal to 1 plus 2 plus 1, which is 4. So f of 2 is 4, so it satisfies the formula. Let's see if it follows for f of 3. So it will be 1 plus f of 2 plus f of 1. So it will be 1 plus 4 plus 2. So it turns out to be 7. So it holds for f of 3, and if you check again, it will hold for f of 4 as well. So I can say that this formula gives the lower bound of the number of nodes in the AVL tree. So now we have this formula. Also I can say that f of h minus 1 is greater than f of h minus 2. So if I put this equation in this equation, I will get f of h is greater than 1 plus f of h minus 2 plus f of h minus 2. Or I can say that f of h is greater than twice of f of h minus 2. Let's name this equation as equation 1. If I put h minus 2 in equation 1 instead of h, I will get f of h minus 2 is equal to 1 plus f of h minus 3 plus f of h minus 4. Also we can say that f of h minus 3 is greater than f of h minus 4. So similarly we can say that by putting this equation in this equation, f of h minus 2 is greater than twice of f of h minus 4. Now let's name this equation as equation 2 and this as equation 3. So from 2 and 3, we can say that f of h is greater than 4 times f of h minus 4. And if we keep on doing this, we'll get f of h is greater than 2 power I into f of h minus 2i. Also we know that f of 0 is equal to 1, right? This is the base case. So let's put h minus 2i as 0. So from here we'll get I is equal to h by 2. Let's put this in this equation. So we'll get f of h is greater than 2 power h by 2 into f of 0. So now we have f of h is greater than 2 power h by 2 into f of 0, and since f of 0 is equal to 1, I can write like this. And since f of h is the minimum number of nodes in the tree, let's replace f of h with n. So it will become n is greater than 2 power h by 2. And if I take log both sides with base 2, I will get log n is greater than h by 2. So I can say that h is less than 2 log n. So from here, using this, we either found out the lower bound of n, or we found out the upper bound of h. So now let's find out the lower bound of h as well. So for that, we'll have to look for the maximum number of nodes in the AVL tree. So now let's look at what is the maximum number of nodes in an AVL tree. So an AVL tree could have maximum number of nodes if it has both the left child and right child for each node, correct? And since it has both the left child and right child, it will be a balanced AVL tree. So we can extend this up to height h. So at height 0, the number of nodes is 1. At height 1, the number of nodes is 2. At height is equal to 2, the number of nodes is 4. At height 3, number of nodes are 8. So here I can say the number of nodes is 2 power 0. Here it is 2 power 1. Here it is 2 power 2. Here it is 2 power 3. And so it will go on up to 2 power h, correct, where h is the height of the tree. So the total number of nodes will be 1 plus 2 power 1 plus 2 power 2 plus 2 power 3 up to 2 power h. So if I take 2 power h common, it will become 1 plus 1 by 2 plus 1 by 2 square up to 1 by 2 power h. So it's a GP, and if we solve this here, we can say that 2 power h into 1 into 1 minus 2 power h plus 1, 2 power h plus 1 upon 1 minus 1 by 2. Upon solving this, we will get total number of nodes is equal to 2 power h plus 1 minus 1, and hence the maximum number of nodes will be 2 power h plus 1 minus 1. So we can write n is less than or equal to 2 power h plus 1 minus 1, where equality holds when n is the maximum number of nodes. So I will take 1 here, and it will become n plus 1 less than equal to 2 power h plus 1. I will take log base to both sides, so it will become log of n plus 1 less than equal to h plus 1. Taking 1 that side, it will become h is greater than or equal to log base to n plus 1 minus 1. So this is the lower bound of h, and we had the upper bound of h. So h is now greater than or equal to log n plus 1 minus 1 and less than log n. So I can say that h is approximately of the order log n. And since AVL tree is a binary search tree, and in binary search tree most of the operations take order of h time, in AVL tree operations will take order of h times, and so the time complexity in AVL tree will also be of order log n.